Okay, this is a video about solving trig equations. Before we get started on some examples, I just want to share a few insights that I've had as I've taught this material before. Um, I think that part of the problem with solving trig equations is algebra, and then there's part of it that's trigonometry. So I want to talk mainly, we'll address both, but right now I want to talk about the trigonometry part. Recognize that like a lot of equations, you're just manipulating, you're using properties of equality, you're squaring both sides, or you're factoring. These are all algebraic maneuvers involving no trigonometry at all, and you eventually get down to, sine of x equals a number, or cosine of x equals a number, or tangent of x equals a number. And so I just want to talk about how those functions can be thought of graphically so that you have something in your mind when you're working the algebra. So I'll devote the left graph in red to sine, the middle graph to cosine, and the green one to tangent. So you've worked the algebra, you've done everything you can until you get down to sine x equals something, and you're trying to figure out how many solutions and how to find them out. Well, if you have sine of x equal to a positive number, I want you to think about having isolated a positive y coordinate, because that's what the sine is keeping track of. So if the sine of x is equal to 1/2 or 0.7 or 0.4, your horizontal line is going to be somewhere above the x-axis here. And you'll see that there are two points on the circle that will have that y coordinate. One's going to be in the first quadrant, that's that angle, or marked by that angle, and then we have this one really marked by that angle. Okay? So you see we'll have a quadrant 1 solution and a quadrant 2 solution. Okay, that's when the sine of x is positive. If the sine of x is negative, then you'll have a horizontal line down here, and you'll see you have a quadrant 3 solution and a quadrant 4 solution. My point is, though, that your calculator will spit out the first quadrant angle, or in your mind, you might have a reference angle that you know that the sine of x is equal to a half, then you know that the reference angle for that is pi over 6. But you still need to figure out how to get the second quadrant angle. And I just want you to look at this picture and recognize that this angle, whatever it is, even if it's a irrational, unfriendly number, the relationship still holds that this angle over here is identical. I mean, these have to be the same angle. So you would say that whatever angle this angle is that much short of 2 pi, or sorry, pi, or 180 degrees. Okay, so for example, if this one's 27, this is 180 minus 27. That's that angle. Okay, so these two angles are the same. If this one's 27, this one is 180 minus 27. If this is pi over 9, then this is pi minus pi over 9, or 8 pi over 9. So generally, you're going to get solutions like theta and pi minus theta. It even works for an angle like 210 degrees. You'll have 210 degrees, and then you'll have 180 minus 210 degrees, which is negative 30 degrees. And that's going to be your fourth quadrant angle, expressed as a negative number, but you can then fix that to call that 330 degrees. Okay, cosine is going to work very similarly. Instead of having a horizontal line, we're going to do a vertical line because you're isolating a particular x coordinate. And you'll see that you have a solution here and a solution here. So there's this angle that has a solution to that intersection, and you have this angle that marks that intersection. So again, you recognize that there's this angle, and then there's this angle again on the other side, marking how much short the big angle is of 2 pi. So you'll have theta, and you'll have 2 pi minus theta, finding the fourth quadrant. So here we have a quadrant 1 solution, and we have a quadrant 4 solution. That's when the cosine of the angle, that's when you have a positive, cosine of x is equal to a positive number. If you have a cosine of x equal to a negative number, you draw a line over here, and you'd see you have a second quadrant angle and a third quadrant angle. But again, it's going to be 2 pi minus that second quadrant angle is going to give you the third quadrant angle. So 2 pi minus and pi minus are very helpful for cosine and for sine. Okay, so then tangent can be thought of as the slope that this radius makes. Okay, so the tangent of that angle can be thought of as the slope that this radius makes with the positive x-axis. So whatever that slope is, we know that it's positive. It's going to be repeated over here. Okay, so this radius obviously has the same slope as this radius, so we have that angle and we have that angle producing radii that's of identical slope. And so you notice that we'll have theta for that first quadrant angle, and then we'll have this third quadrant angle over here represented as pi plus theta, or 180 plus theta, because we're going to go diametrically opposed angles. So you get those by adding 180 or adding pi. So positive slopes happen in the first and the third quadrants, and negative slopes happen in the second and the fourth quadrants. Why the tangent can be thought of as a slope is a proof for a different day, but that's a good thing, very handy thing to think about when you're solving equations. Okay, so on to actually solving some equations. I've written the work out already. I just want to walk through. I've picked out a couple of examples, worked them through, and I just want to talk to you about this one. I chose this one because it has a double angle for cosine, and that's often a tricky spot for students, knowing that the cosine has three options. Okay, this first one comes from the law of cosines. Your teacher hopefully showed you when you proved the double angle for cosine. And then the other two fall right out when you use Pythagorean identities, like sine squared x plus cosine squared x equals 1. You can create these other two options for the cosine of 2x. Okay, so you're looking at this equation, you're wondering, well, which one do I choose? You look at this appearance of sine, and you quickly recognize that you'd like everything to be in terms of sine. You don't want a cosine x and a sine x. That makes it hard to solve. If everything's in terms of sine, then you can do some work. So I did that right here. I substituted 1 minus 2 sine squared x, which is this top identity, for a cosine of 2x. Down here, I subtracted the 1's. Next step is I took the opposite of both sides, all legal operations. Another temptation here that students have is to divide by sine x. But the string you have to have on your finger to remind you is that if something could be equal to 0, then you can't divide by it, because division by 0 is a big no-no. So the sine x could be equal to 0, and that would actually make the equation true. You'd have 2 times 0 squared equals 0. That's true. Okay, so I can't go dividing by a quantity that could be 0. So anytime there's an unknown quantity, you really shouldn't be dividing by it, because it could be 0. Okay, so instead I subtract and factor. So I subtract the sine x from both sides, I factor out a sine x, and I get this is the end of the algebra. Okay, well, I guess invoking the zero product property over here is really the end of the algebra, but from here on is the trigonometry. Okay, so sine x equal to 0. I'm thinking about the unit circle right now. The sine x is equal to 0. When is the y coordinate 0? Well, here, and then back here again. Usually our solutions are 0 to 2 pi, including 0 and 2 pi, so that's why I have 3 solutions here. This one says sine of 2 sine x equals minus 1 is equal to 0. That's saying that sine of x is equal 1/2, which is like up here. So I'm going to have a first quadrant and a second quadrant solution. I know my trigonometry well enough to know that that 1/2 comes out of a right out of a 1, 2, root 3 triangle, which is a 30, 60, 90 triangle, and that reference angle is going to be pi over 6. I just know that, and I don't think the point of this video is to help you know that. That's just something you need to work on, learning some reference angles. The second quadrant angle is going to be pi minus pi over 6, or 5 pi over 6. Okay, so there's 5 solutions to that equation. There's the algebra, and then there's the trigonometry over here. Okay, this one I chose because it has a Pythagorean identity involved. So if we just look at the equation, ignore the stuff here. Just look at the equation. I've got appearance of sine squared, appearance of cosine squared, and appearance of sine x. So the squareds tip you off that you should use the Pythagorean identity. Sine squared plus cosine squared equals 1. And I'm going to choose to use cosine squared is equal to 1 minus sine squared, so I can express all of the functions in terms of sine squared. So I replace cosine squared with 1 minus sine squared. All right, there's a little trigonometry there. Now I'm going to do some algebra. I'm just going to solve for 0. I'm going to get the equation equal to 0 by adding and subtracting both sides of the equation. And I get 2 sine squared x minus sine x minus 1 is equal to 0. And that looks messy to some students, so I urge them to just substitute the sine x, let it equal m. And so you pack up sine x in a suitcase and you ignore it for a while, just doing the algebra on the abstract forms. 2m squared minus m minus 1 equals 0. That factors nicely into 2m plus 1 times m minus 1 equals 0. So 2m plus 1 equals 0, or m minus 1 equals 0. M is equal to negative 1/2, or m is equal to 1. And then you unpack the suitcase and you get sine x back. Sine x equals negative 1/2, sine x equals 1. That's just the algebra. Over here, I'm going to solve these equations. Sine x equal to negative 1/2. That happens down here in the third and fourth quadrants. Reference angle is still pi over 6, and I know I'm 1 pi over 6 past pi, which is 7 pi over 6, and then 1 pi over 6 short of 2 pi, which is 11 pi over 6. And the sine of x is equal to 1 at the top of the circle there at pi over 2. So here I have 3 solutions. Okay, moving right along. Again, this temptation to divide by sine x has to be ignored. You have to resist the temptation to divide by sine x. Instead, you have to subtract and factor. Okay, so I subtract the 3 sine x, I factor out the sine x equals 0, or tan x minus 3 equals equal to 0. Okay, so now I'm doing the trigonometry. Sine of x equal to 0, we've done that one before, 0 pi or 2 pi. This is the one that I'm interested in. The tangent of x is equal to 3 somewhere in the first quadrant. Some angle makes that radius have slope 3. And then somewhere again in the third quadrant, the slope of 3 is going to be repeated. I don't really care what the value of that angle is, the approximate value. Inverse tan of 3 is really the only way to express that number exactly. And I just know that I need to add pi to it to get to the third quadrant. And I don't really want to approximate these numbers. I don't need to pick up my calculator. I don't have an incentive or a reason to approximate that number. If this equation were part of a much bigger contextualized problem where I needed to know the angle of elevation of a cannon being fired, of course, then I would approximate the number, because if somebody asks me what's the angle, I'm not going to tell them the inverse tan of 3. I'm going to tell them 66 degrees or whatever that is, approximately. But I don't have a need to approximate, so I'm not going to. I just move right along. It's quicker to just leave my calculator alone and know that I have the inverse tan of 3, and then I have pi plus the inverse tan of 3. 5 solutions. 1, 2, 3, 4, 5. Okay. I chose this one because a lot of students play around with these equations trying to get sine over cosine to get tangent, but this plus 1 over here is going to prevent you from really isolating to tangent. You're either going to have sines and cosines, or you're going to have secants and cosecants. And the thing to do here is to square both sides, so that you can then invoke the Pythagorean identity. So if we square both sides, we get 4 sine squared x equals cosine x plus 1 quantity squared. So I'm just doing some algebra. 4 sine squared x is equal to, and I just multiply this binomial out. I get cosine squared plus 2 cosine x plus 1. Then I'm going to invoke the Pythagorean identity here. I'm going to substitute 1 minus cosine squared x for sine squared x, so I can get everything in terms of cosine. I distribute the 4, and then I collect like terms solving for 0, solving equal to 0. And I get 5 cosine squared x plus 2 cosine x minus 3. Adding 4 cosine squared and then subtracting 4. Lucky for me, that factors nicely into 5 cosine x minus 3, cosine x plus 1. Notice I didn't pack the cosine into a suitcase like m or something. You can do that if you'd like. It really it makes things look a little easier, but once you get good at it, I don't think you really need to do that anymore. Okay, so 5 cosine x minus 3 is equal to 0. Cosine x is equal to 3/5. So I know that I have a first quadrant angle and a fourth quadrant angle. I don't really care, again, what the value of that angle is. I just know that the inverse cosine of 3/5 is in the first quadrant, and then 2 pi minus that is going to give me the fourth quadrant angle. If somebody wants me to approximate it, I can do that. I can just type in inverse cosine 3/5 and then type in 2 pi minus it, and I'll get the other ones. But there's no real need to do that in this problem because it's just a math problem asking for the exact solutions. And if you approximate them, then you're not giving exact solutions anymore. Okay, the other factor is cosine x plus 1 equals 0. So the cosine x equals -1. That's that spot right there because we want the x coordinate equaling -1. And you get x equals pi. 3 solutions. 1, 2, 3. Okay, last but not least, having the variable angular velocity here. So if you watch my other video on angular velocity, I think it'd really help you. Maybe you should pause here and go watch that one. Because a lot of students get really tripped up when there's a factor inside inside the sine or the cosine or the tangent. The way you should think about it is that 3 suggests that the point going around the circle goes 3 trips around the circle as x varies from 0 to 2 pi. So think about it. X goes from 0 to 2 pi. 3x goes 0 to 6 pi. 6 pi is 3 trips around the circle. So if you think about a horizontal, a horizontal line here at root 2 over 2, okay, there's a solution and there's a solution. But if we go 3 times around the circle, I'm going to have 6 solutions. 3 times hitting here, 3 times hitting here. Okay, so what I do is I just solve the equation for 3x. Okay, I say 3x is equal to inverse sine of root 2 over 2. And I know that's pi over 4. Okay, and I know that the second occurrence is 3 pi over 4. That's going to be my second quadrant angle. Okay, so 3x, I'm not solving for x, I'm solving for 3x. And I know that I have to go 3 times around the circle. So 2 pi past this one the first time is going to be 9 pi over 4. That's just 8 pi over 4 plus pi over 4. And then 8 more pi over 4 is going to be the third incident of this angle here. And then 3 pi over 4 is going to have 3 incidents also. 3 pi over 4, 11 pi over 4, and 19 pi over 4. So this row represents the 3 solutions on this spot on the unit circle. And then this row of 3 represents the 3 solutions at this spot on the unit circle. The first quadrant ones and the second quadrant ones. And then when I solve for x, I'm essentially dividing both sides of this equation by 3. I'm dividing every single one of these angles by 3, which basically just changes their denominator to be 12. So that's all I did here, was change all the denominators to 12. And then lastly, I think these two can be simplified to 3 pi over 4 and pi over 4. And I have 6 solutions. Notice that these are no longer, once I divide by 3, I can't call these first quadrant and second quadrant solutions because they moved. When I divided by 3, I took a third of the angle, which could have changed what quadrant they're in. And this should line up nicely with your idea of the sine of x having a graph like this. I'm going to draw 3 periods of it. Okay, so this is 0 and this is 6 pi out here. And then this is sine of x. And when I compress to be the sine of 3x, which is a horizontal compression, that's 2 pi. That's 2 pi. I'm actually going to have 3 periods smushed into two pi. This is the sine of 3x. And you can see that root 2 over 2 is a horizontal line. You know, if the function is equal to root 2 over 2, I'm essentially drawing this. I'm going to have 2 solutions here on this graph between 0 and 2 pi, and I'm going to have 6 solutions on this graph between 0 and 2 pi. And what I'm saying is a third of this one is here, a third of this one is here, a third of this one is there, a third of this one is here, a third of this one is there, and a third of that one is there. So for you graphically minded people, there's just a mapping going on. It's a shrinking of a factor of 3, and each point gets mapped to a point a third of the distance away from the origin. Okay, so I went a little quickly there, but you can rewatch it if you need to see it again. Hope that helps.